Okay, this video we are going to talk about um, internals of Tokio. So if we take the Tokio program, so I downloaded the Tokio module, the crate here, and this is what we have, the full Tokio crate. And as we discussed in the last video, Tokio comes with multiple crates: Tokio macros, Tokio stream, Tokio test Tokio util. So in Tokio, specifically, if we look into that, Kagado we can see that Mio metal IO is one of the dependency. So this is the backbone for Tokio um, systems. So how that is, the Tokyo stack. This is a good blog to read through Tokyo internals. Some of the things might have changed, but um, this is something um, good to read. So when your program it's connected to Tokyo and it's touch Mio, Metal IO and futures, and internally it calls the system selectors, system calls epoll kq. Epoll is for Unix, kq is for FreeBSD, I think, and IOCP is for kq is for Mac as well, I think. IOCP is for Windows. So Tokyo Stack System Selector, each operating system provide facility for receiving IO events. So epoll Linux, KQ Mac, IOCP for Windows. Metal IO is a Rust script that provides a common API for low-level IO by internally handling the specific details for each operating system. So Mio will help us to abstract the system calls. We can just use its event loops and connection, so that will abstract away as the operating system's specific system calls. Futures, yeah, we are using futures for async. So powerful abstraction for representing things that have yet to happen. This abstraction is general enough to be used for many things besides IO. Yeah. And Tokyo Core Crate provides central event loop, which integrates Mio to respond to IO events. Yeah, Mio needs to have an event loop, um, so that is abstracted, built inside Tokyo Core for Tokyo. Inside Mio, we have Ball and Evented. I think these things got changed now. If you go here, event, yeah, go to latest version. Now events are struct, and event is a readiness state paired with token, and it is returned by poll function method. So first, yeah, that is one thing, and let us go to that part as well. Yeah, Mio supplies the evented trait. I think this has changed now. But the call to Mio poll, I think this thing is still there. Yeah, it's still there. Wait for readiness events. Block the current thread and wait for readiness events for any of the event source that has been registered with the poll instance. Yeah, for that, let us open VS Code and open Mio as well. We can run the example code. Uh, this is the same example we have in Mio Crate. So here we are using stderr, and MioNet will give you TCP listener and TCP stream, and Mio provides events. Events are, let's go to events. A collection of readiness events. Event is passed as an argument to poll and will be used to receive any new readiness events received since the last poll. Usually single event instance is created at this time as poll and reused on each call to poll. Okay, events, system events. Yeah, it's internally calling the system events itself. So if you go to system, let's go to this events. This is inside systems in Mio. So this is a struct which has a raw IO event completion, box complete status, and events, vector of events. Let's see where this is defined. It's a flag and data use 64, and it has a token. We can pass token function with events. Implement event new define with token. Okay, and poll receive, poll send, different flags. Okay, so Mio, let's go to Mio module. Do we have Mio open here? No, let's see. Yeah, this is Mio. Let's go to Mio and SRC and sys. Sys is where we found that, and Unix and pipe is there. TCP. Let's see how TCP is implemented. So you can see sys Unix, new socket, socket address, all these things are imported. Here they are calling that syscall. They have a syscall macro, which is used to call the internal actual system calls. Yeah, connect here. You can see raw FT address and length. So this is basically if you see socket connect, socket system calls. Yeah, socket. Let's see what all things we have here. Socket connect. Connect will have socket FT and address and length. So basically that's what it is getting called here in Mio. So internally they are calling that system calls. So that's what Mio is abstracting. And so how we came here? Yeah, from here. Uh, yeah, events. Yeah. So what we need to do in order to run a TCP connection, server and client, we need to define token for server. I'm defining 0 as server, client as token 1, and we need to create a poll instance, and we need to define events with how much is the capacity and the address. Events with the capacity address we are defining. This is the server address, so we are binding that address with server, and we have to register that um, server to the poll registry. That's what we are registering here. So let's see what actually this is. Registry, create a separate registry we can which can be used to register events sources. Wait for readiness events. Block the current thread and wait for readiness events for any of the event source that have registered with poll instance. The function will block until either at least one readiness event has been received or timeout has been elapsed. So that's what that is. And we are creating a client with TCP connect to the address. So we will get a client and we are registering that client also to this poll registry, and we are doing a loop. So this is the events loop. We are looping and getting any events, o- polling all the events and iterating through each event, and match event token, anything has any match. If it's 0, then it's a server, so that will be server connection. We accept that connection and print. If it's client, we are actually basically not doing anything. So let's run this and see. Yeah, so we got the client TCP stream from this, and peer is this, and this is what our server is. And server received that connection from that client, so it's print out that too here and dropping the connection. So that's a basic example of Mio structure, and you can see a lot of Paul registry. This loop is manual loop, these kind of things. This will be abstracted in Tokio core. So let's see what is there in the Tokio core as well. Do I have that opened? Yeah, Tokyo. But I didn't see the Tokyo core. Where is Tokyo core? Oh, Tokyo core might have moved out. What he mentioned might have a long back source code. So let's see where it has IO. It's in IO. Process runtime task. Okay, where he has mentioned that. Connection features. Okay, yeah. Poly vendor non-system system selector. Mio provides cross-platform access to system selector. Okay, that we have discussed. Non-system. In addition to providing readiness for Mio can also indicate readiness events generated in user space. Hmm, Create more. So he has explained in that sample program what we have seen, and he's also explained what is futures. Yeah, it will notify the futures executor. So Tokyo's interface with Mio. Tokyo convert task notification into Mio events. So yeah, that's where it's getting integrated. The futures notification uh, task and their futures require an executor to run. An executor is responsible for polling tasks future at the correct times, usually when it has been notified that progress can be made. Such a notification happens when some other code calls to notify method of the provided object implementing future executor notified trait. So notify.park, wait for internal future to complete, blocking this thread's execution until it does. This function will call poll future in a loop, waiting for the future to complete. When a future cannot make progress, it will use thread park to block the current thread. Yeah. So Tokyo put that notifications. So here we are defining a struct my set readiness. It's a Mio set readiness. Set readiness is there. Mio. Let's see. We have set readiness. I think that might have changed totally. Uh, readiness interest. It has a vehicle. Let's see that Mio code source code. Where is it? It's in the set readiness. Yeah, this is Tokyo core. Oh, now it's changed to reactor. Is that so? Yeah, reactor mode. Poll evented. Timeout. Mio events. Yeah, core is. Oh, it's inside reactor here. So we in reactor we can see the struct core. This is the event loop. Event loop is the main source of blocking in an application which drives all other IO events and notifications happening. Each event loop can have multiple handles pointing to it, each of which can then be used to create various IO objects with the event loop in interesting ways. So we are keeping Mio events here and TXMPSC transmitter, receiver, and registration and readiness. Yeah, my set readiness is here. Where's this set readiness is coming from? It's just arc. Yeah, it's my Mio set readiness. Mio should have a set readiness then. That's readiness. Yeah. Updates readiness state of an associated registration. Registration for documentation on using set readiness. Handle to user space poll registration. Registration set readiness. Okay. So coming back to that original documentation. So we are creating a set my set readiness implement notify for my set readiness. Notify from the future, right? Yeah. Let's see what we have here. Future task. Control notify. Hmm. Notify for my set readiness. Okay, let's see. Notify. What is that thing? Notify future. First. Yeah, Tokyo sync features notified. Implement notify. Notify. Struct available on create feature sync only. Notify provides a basic mechanism to notify a single task of an event. Notify itself does not carry any data. Instead, it is to be used to signal another task to perform an operation. Okay, so notify, std sync arc notify, notify clone, Tokyo spawn, and we are putting the second one here and awaiting it and saying receive notification and println sending notification and notify dot notify one. Yeah, notify one, notify the first waiting task. Okay. Hmm. So this will be notified. So that's what happening here. What was that? Oh, we lost that. Mio, Tokyo, futures, Tokyo, Mio. Yeah, here. So we are notifying, notify, set 0, set notify, ready, Mio ready readable. Okay, so we are set readiness for this Mio ready readable. In this way, task notifications are converted to Mio events and can be processed in Tokyo event handling and dispatch code along with other type of Mio events. Just as Mio wraps stdnet struct such as UDP socket, TCP, and TCP stream to customize functionality, Tokyo also uses composition and decoration to provide Tokyo aware versions of these types. Yeah. So this is what Linux actual file descriptor, stdnet UDP wrap on it, and Meiosis UDP socket will wrap this stdnet UDP socket and implement evented on this. I think this might have changed slightly, but yeah. And Tokyo Core Reactor is um, implementing the poll evented on top of it, and that this type will be used as Tokyo Core Net UDP socket. actually. Tokyo version of this IO source types provide constructors that require to handle event loop. Let's see what we have here. When instantiated, these types will register their sockets with event loops epoll to receive edge-triggered events with a newly assigned even number token. Oh, I don't know, even number token. Yeah. So flowchart outlines basic steps of Tokyo even loop. Core, run future, spawn a task of the provider future. This is main task. Poll the main task and its future. Did the future return ready? No. Then calculate the timeout duration based on the next timeout event, if any. Then call meopoll. This blocks until events are available. Timeout duration has elapsed. Handle any timeout that are due. Are there any events to process? Yes, process next event. What type of event is this? Token message, clear readiness and process message. Token future, clear readiness, not the event. IO source ready, notify the IO reader and writer task. Spawn task ready, poll the associated task. And pass that are these events to process? No, then go back. Was the token future received? Yes, then inform the main task. Poll the main task, its and its future. This high level makes sense. Tokyo, it's polling Mio and Mio events and future epoll wait Linux struct epoll event coming back to Mio events notify schedule reader task notify set readiness Mio add new event to the readiness queue. Yeah, when you set the readiness. Tokyo event loop calls meopoll, which in turn call epoll wait, Linux epoll wait, which block until some readiness change event occurs on one of the mounted file descriptors. When this happens, epoll wait returns an array of epoll event structs describing what has occurred, which are translated by Mio into Mio events. Mhm. Yeah, basically internally that is what happening in Tokyo. So let's go back to Tokyo again. So Mio is one of the dependency and that's nice. Socket. IO result socket to type. Okay, this is what basically I thought of covering. Anything else? Okay. Um, epoll is the event loop. Um, yeah, Yeah, this is one of the good document. I've seen one blog as well. Yeah, this is something good to read. Good new book, Linux programming interface. Yeah, this will be a good one to read. Yeah, and epoll. Yeah, this is AP modern. No, this one I thought of giving another documentation. Not this one. Yeah, this one. This is also a good to read. How important, how crucial epoll is for async programming. So yeah, that's all I need to cover in this video. We will connect in the next one. Thank you.